Alright, so let's get started with this. Well, so last time we were about halfway through integration by parts, or maybe just the beginning. We got to do a couple of exercises, and well, so we stopped where we finished example B. So let's look at letter C. So one more example, integration by parts. Well, again, I will be constantly writing our acronym to help us get the U of the problem, so we can also get the DB part. And also I will be writing the formula, so we don't have to either flip between pages or scroll up and down on the screen. Okay. So again, the LIATE acronym is helpful to let us choose the U in the setup. So number one, okay, let's see our U. And even though it's technically not a product of two functions, it is in a way, because it's an invisible one right here times the arctime, so there's technically two functions there. Anyway, number one, let's look at the checklist. So the LIATE is going to be our checklist to set the U. So L stands for logarithmic functions. Do we have any logarithmic functions in our integrand? No. What's the next? I. What does that stand for? Inverse trigonometric function, not just any inverses, right? So it's important to be precise with what the I stands for. So do we have any inverse trigonometric functions? Yes. Yeah, so that's our U. In fact, even if you say, oh, dv equals arcsine x dx, isn't it the original problem? I mean, so that's not actually what it is. Well, dv should be dx. Well, the derivative of arcsine x, that's going to take us back to Calc 1. Any ideas on what that derivative is? 1 minus x squared. And well, the integral of dv is v, the integral of dx is just x. Alright, let me make this smaller. I might need space later. Okay, so let's go back to the original integral, and in accordance with the formula, u times v, that is arcsine x times v, which is x, minus the integral of v, which is x, times du, which is 1 over the square root of 1 minus x squared dx. Okay? Again, one thing at a time. Let's clean up all the parentheses and all that. Number one, so let me write this x in front of the arcsine, and at the same time get rid of these parentheses. So this will be x arcsine x minus the integral of x over the square root of 1 minus x squared dx. Okay? Well, the first term we're done. We don't have to do anything about it, so that's fine. And well, what about the integral at the very end? So any ideas on how to compute that integral? U substitution. This is a really good candidate for U substitution. Observe the degree inside of the radical is 1 more than the x that we have multiplying with the dx, so that's going to work just fine. So that's u equals to 1 minus x squared, du will be negative 2x dx. That means x dx equals negative 1/2 du. Alright? So, let's see. Let's write this integral in terms of u's. So, well, that's going to be x arcsine x minus the integral of, well, this x dx becomes negative 1/2 du, and that's the square root of u in the denominator. Well, a couple of things to do here. Number one, let's clean up the product of negative signs. That's a negative times a negative, which will be positive. Also, I'm going to take this 1/2 outside of the integral, and I'm going to go back to the radical form. well, I'm going to write that radical in the denominator as u to the 1/2, but I cannot still integrate while it's in the denominator. So in this case, we will move it to the numerator with negative exponent. Okay, that's going to be u to the negative 1/2 du. And well, this is just a general power rule problem. Add 1 to the exponent and divide that by the new exponent. Well, so that's x arc sine x plus 1/2. What is negative 1/2 plus 1? 1/2 divided by 1/2. And check this out. Check how these 2 halves go away. And in the end, that u to the 1/2 becomes a radical again. So x arc sine x plus the square root, and in this case at the same time we may go about the back substitution, and that's our final answer. Okay. Questions? Okay, what about it? Oh yeah, let me keep it for one more second here, for a few more seconds. All right. Let me know when you're ready for the next one. So in so many cases, we may need to perform the integration by parts more than once, and that's the next problem. Well, for these first 3 examples, we look at different kinds of exercises, how we choose the u and the dv based actually by using the help of the LIATE acronym. Well, so let's see. Let's see what about repeated integration by parts. And again, keep using LIATE. Right, then let me write the formula again. Well, let's go with the checklist. L stands for logarithmic functions. Do we have any logarithmic functions here? No. Okay. I stands for inverse trigonometric functions. Do we have any? A. What does the A stand for? Algebraic function. Do we have any algebraic functions? Which one is it? That means dv will be sine 2x dx. Okay, differentiate the u, integrate the dv, so that's du equals to 2x dx, and v equals to, what's the integral of sine? Negative cosine 2x, and I left the space for the 1/2 factor that comes from the integration. All right. Well, from here, what are we going to get? Well, we have everything ready for the integration by parts. All right. So let's see. U times v, that is x squared times negative 1/2 cosine 2x minus the integral of v, which is also negative 1/2 cosine 2x, times du, which is 2x dx. Right? And again, just to briefly check the consistency, this is u v minus the integral of v du. Right? Well, so before attempting to compute the integral that we have here, how about simplify as much as we can? Okay, number 1, I'm going to write this negative 1/2 in front of the x, and I'm also going to get rid of the parentheses. But also check this out. This 2 cancels with that 2 because one is in the numerator, it's multiplying, the other one is dividing. Their inverse operations, they cancel out. And then from here, okay, so that's negative 1/2 x squared cosine 2x, and negative times a negative is positive 1/2 outside, integral of x cosine 2x dx. And well, in this case, this integral right here, unlike the previous example, yes. Yes, that's what yeah, that never happened. Yep, that never happened. Nothing to see here. Move along. All right. So, okay, the integral of x cosine 2x. Well, let's go back to the previous example. In the previous examples, we were able to use some u substitution to compute, or actually a very tiny u substitution to compute the second integral that arises after using the integration by parts. In this case, well, if we check this integral right here, unfortunately, the integration by parts method, the u substitution method, it's not going to work. It would have worked if we had 2x squared right here, because if we set u as 2x squared, du would have been 4x, and well, we have that x multiplying with the dx, and in that case it would have worked very perfectly. Well, it's not the case, unfortunately. So this is another candidate for an integration by parts one second time. So let's go ahead and do that integration by parts one more time. All right. Okay, let's use this color. So u, again, in this case, the algebraic is going to come first. dv equals cosine 2x dx. du will be then dx, and v equals to the, what's the integral of cosine? Positive sign, right? That's the positive sign, 2x and times 1/2 outside. Okay, so we have everything ready to compute this integration by parts. So negative 1/2 x squared cosine 2x plus whatever we get from this integration by parts. And let's see, that's u times v, that's x times 1/2 sine 2x minus the integral of v du. Number one, let's clean up parentheses. I'm going to write this 1/2 factor in front of the x, sine 2x, and then minus 1/2. I'm going to take that constant outside of the integral, and that's the integral of sine of 2x. And this integral, this baby integral, we already did it here in the first time we set up the u, the integration by parts. So negative 1/2 x squared cosine 2x plus 1/2 x sine 2x. And then careful here, check this out. Number one, what's the integral of sine? Negative cosine times the negative in the front. We'll turn that into a positive. Well, that's a 1/2, the one that we already had it, times the 1/2 from the integration sine 2x plus c. But how about we just go with 1/4, because 1/2 times 1/2 is indeed 1/4. All right? Yes, that's what I meant, but not what I wrote. Thank you. All right? And I'm missing the plus c. And that's our final answer. All right. So that's one example in which we need to use integration by parts more than once. For example, what if we had this integral? How many times would we need to do this setup for the integration by parts? Do you feel like doing it? Not really, right? Well, what I want you to see anyway is that typically this power of x, it's going to tell us how many times do we need to carry the integration by parts as we try to simplify the integral over and over. Of course, we're not going to do anything with a power this huge. Come on, that's going to take the entire weekend, right? So Let's see. Let's look at another problem, a very, very special problem. Whenever we have the integral of an exponential times a trigonometric, in particular just sine and cosine, note, treat it as an equation. You'll see why. What do we mean by treating it as an equation? Well, notice all the problems that we have done before. So we start with the integral, we just write equal, whatever, equal, so we just go with the line, we just go with the flow until we get to the final answer. And we never write the original problem anymore again, we just go with the flow, write down the final answer. However, this problem will be different, and you will see why. You will see why instead I will constantly write the original problem again, so it looks like we are solving an equation. So let's see. So number one, another thing here. The Liata thing is not going to work here, or actually it's going to work either way. It doesn't matter if you choose the exponential as your u or the trigonometric as your u. So in this case, I'm going to go with u equals the exponential, even though technically the t for trigonometric comes first and then the e comes last. I'm going to do the exponential first. And that sine, hold on. That's dv equals sine x dx. So the derivative of the exponential, which is itself, times the derivative of the exponent, which is 2. Derivative of 2x is 2. And then dv, we're going to get v, which is the integral of sine, and that's negative cosine x, right? So we have the 4 parts right now. Okay, let's get it done. Let's do the usual. Set up, use the formula u times v, that is e to the 2x times negative cosine x minus the integral of v, which is negative cosine, times du, which is 2 e to the 2x dx. Alright? And I strongly recommend you use all these parentheses right here, because what if you don't use these parentheses right here? This one is not going to look like a product of the functions. In fact, it's going to look like a difference, right? And you may get confused with the result. If this were definite integral, you will get a different result. Or if you put this in your blank spaces on WebAssign, it's going to take it as incorrect. So that's why it's important to have these parentheses to still denote this as a product. Question? If I put the negative sign in front of the 2x power, is that? It's fine. I mean, if you want to do like everything from the first step, like in your head, that's fine. But I'm just showing all the steps as a suggestion. So in the case that something doesn't check in the end, you have all the work, every single step, and just checking. It's here, you know. So let's see. This will be equal to. Okay, let me continue here. Notice I'm not going to go with the line. I'm going to write the whole problem. I'm going to write the original problem, e to the 2x sine x dx, and this is negative e to the 2x cosine x minus minus equals to plus, and these two right here, I'm going to take it outside as a constant multiple. Alright, so now let's look at this second integral that we obtained. Well, if we compare the form that we have, this is going to be an e to the ax times cosine bx, alright? That means we are going to do the same setup for the integration by parts. And let me label this as number 1, which is going to be the first, which will denote the first integration by parts, the first setup, and number 2 to denote that this will be the setup for the second part. Alright, so in this case, u equals to e to the 2x dv equals cosine x dx. The derivative of u, which is du, That's 2e to the 2x dx, the same way as last time, and I forgot a dx right here. All right? And this will be v, the integral of cosine. But what's the integral of cosine this time? Positive sign, right? Sine x. Okay, let's keep going with the original problem. The integral of e to the 2x sine x dx equals, well, we already had e to the negative 2x cosine x plus 2 times, okay, here be careful with this, it's 2 times open brackets, and write down whatever we get from the setup of this integration by parts, okay? So that will be u times v, which is e to the 2x times sine x, minus the integral of v, which is sine x, du, which is this 2e to the 2x dx, okay? Alright, again, before attempting to evaluate the integral that we just got, let's clear the bracket. But be careful when distributing the coefficient. This is going to be 2 times this e to the 2x sine x, and this will be negative 2 times multiply with these 2. Okay, don't forget to multiply these multiple constants. So that's going to give us the following. That's negative e to the 2x cosine x plus 2 e to the 2x sine x minus 2, not 2, right? 4. Yes, I was already making that mistake. So that's 4 integral of e to the 2x sine x dx, and this is of course equal to the original problem. But hold on a second, did you notice anything weird here? Exactly, we're falling into an infinite loop. Well, we're gonna get out of that infinite loop with a little trick here. Alright, well, so what did we get? We're getting the exact same integral as the original problem. What do you want to do? Set up an integration by parts again, and then again, keep adding infinitely many terms and never finish the problem? Well, no, we're not going to do that because that's an infinite loop. Instead, that's why we're treating this problem like an equation because, well, for example, x equals to 7 minus 4x. Solve the equation for x, have all the x's on the left hand side. 5x equals to 7, and solve for x equals to 7/5. Alright? That's what we're going to do here, but in this case with integrals, because this integral is of the same form as that integral. And what I'm going to do, add 4 integrals on both sides. What's going to happen here? Cancel. And 1 integral plus 4 integrals, how many total integrals? 5, right? 5 integral e to the 2x sine x dx equals to negative e to the 2x cosine x plus 2 e to the 2x sine x. And well, we can just get rid of this 5 again because we're treating this like an equation. Just divide both sides by 5 or multiply by 1/5 rather. Alright, so that's the integral of e to the 2x sine x dx. This will equal distribute the 1/5, that's negative 1/5 e to the 2x cosine x plus 2 times a fifth, that's 2/5 e to the 2x sine x, and this is the part where we add the plus c. And final answer. Can you stop taking pictures, please? All these are recorded and posted on Canvas. Okay?
Yes.
All right. Questions about this problem? Let me zoom the whole thing out so you can see in case you missed anything. Any questions or concerns about it?
How do you know when to use that trick? Is it when you get an integral that's equal to?
Yes, so that's why I noticed this as a special form. Whenever you had either one of these two, treat it like an equation. However, this situation will come up in the next section, which is trigonometric integration. Well, you'll see how this is going to work. But that's not the only case. There's going to be another one. So the last example on this section, integration by parts, is just to compute. Oh, sure. Yes. Okay. Okay. Example number 4. So it's just to evaluate a definite integral. All the integrals that we did here were just indefinite integrals. And well, I mean, it's basically fundamental theorem of calculus, upper limit minus lower limit. Well, but when it comes to integration by parts, we need to show the notation at certain steps. So again, let's get our u and our dv. So u equals something, dv equals something. So what's the u in this case? X. Well, we already did its integral a couple of times. So v will be sine 2x. du will be dx. And well, v will be the integral of sine, which is negative cosine 2x times a half. All right. So let's see. Using the integration by parts formula, that's u times v, which is x times negative 1/2 cosine 2x. And then in this case, for this first term, since we already finished the integration, we're going to write down the bar to indicate that we are evaluating this from 0 to pi over 4. And well, you might want to wait until we get all the terms ready to do the fundamental theorem of calculus all at once in our final answer. All right, that's my only piece of advice here. So that's minus the integral within the limit 0 to pi over 4 of the quantity v du. That's a negative 1/2 cosine 2x dx. And again, well, before attempting to compute this integral, let's clean up all these signs. Let's write it nicer. And also let me clean negative 1/2 x cosine 2x from 0 to pi over 4 minus the integral of, that's also actually plus 1/2 the integral of cosine 2x with respect x from 0 to pi over 4. And I think we're ready to compute this last integral right here. Doesn't require any second integration by parts setup. This is a very immediate integral. So that's 1/2 x cosine 2x plus 1/2 the integral of cosine 2x times another half. But how about we just write a 1/4? And in this case, no, we're not going to write a plus c. Now that we have all the terms in our final answer, draw one single bar and write down the limits of integration. And then from there, it's pretty much the same. Yes, it's sine, right? Sine. Yeah. So, well, I think we're ready to compute this. So this is equal to number 1. Okay. Upper limit. To evaluate it at pi over 4. So that's a negative 1/2 x, which is pi over 4, cosine of 2 times pi over 4, plus 1/4 sine 2 times pi over 4. Okay? Now let's think about the lower limit of integration, which in this case is 0. Do we really need to write all that evaluation? Let's check this out. Number 1, what happens if we evaluate cosine of 2 times 0, which is, well, it's going to be technically 1, but times 0 is not going to be zeroed out? And what sine of 2 times 0? How about minus big 0? Okay? Minus big 0, and let's just take care of the rest, one term at a time. All right, so I'm worried about this. Let's worry about the cosines first, because we can either get a 1 or negative or 0.
Like if it was not in 0, like just like homework that I showed homework, did we just show that you're subtracting 0, or can you just solve it?
This 0 is fine, unless we had terms that do not give a 0. Well, in that case we need to write them all. So in this case, it's fine. It's acceptable. So that way just save time on the writing, especially on a quiz or an exam, so where time is valuable. So cosine of 0, that'll be 1, but times this x, which is 0, that'll zero out the term. So let's talk about this. So cosine of 2 pi over 4, that's the same as saying cosine of pi over 2. But what's cosine of pi over 2? 0. What about sine of 2 pi over 4, which is sine of pi over 2? 1. Okay, 0. 0 plus 1/4 times 1, which is, 1/4. Final answer. All right. Question. Yes, all these crunching numbers and symbols, but this final result, what does that represent anyway?
That's the area under the equation x sine.
That's the equation under the curve defined by x sine 2x within the limit 0 to pi over 4. That's correct. All right, so this is the end of the section. Let's move on to the next one and do a couple of exercises. Where is it? Oh, it's right here. So the next section is to compute trigonometric integrals. All right, so you already have some notions on evaluating trigonometric integrals, but I mean like pretty basic ones, like ones that require a pretty basic u substitution. Even if we go crazy about sine x to the 200 or to the 275 cosine x dx. So don't let that power scare you, because what do we have? Sine and the cosine outside, which is its derivative. We can simply use the general power rule. That's sine to the 276 over 76, or 276 plus c. It's just a general power rule, very simple. However, this time we are going to have combinations, products, or more specifically, products of trigonometric integrals. And so we have these guidelines here to help us decide what route to take when it comes to set up these integrals. So number 1, you want to look at the powers of the trigonometric functions. And number 1, whenever the power of cosine is odd, save one cosine factor and use this trigonometric identity. On the other hand, if the power of sine is odd, save one sine factor and use the trigonometric identity the other way around. Well, where is this trigonometric identity coming from? This one is one that you sure know by heart. Sine squared plus cosine squared equals to 1. Depending on their needs, we may need to solve for sine squared, or we may need to solve for cosine squared. Now, It gets a little tricky whenever the powers of sine or of both sine or cosine are even. Whenever we have even powers, we would need to use the half angle, or what we usually call the power reduction formula. All right, so let's see. What about this power reduction formula? So that's to reduce the power. So if we have sine squared, the identity is 1 minus cosine 2 theta, and positive when we have the cosine square. So what we do is reduce the power so we can have a simpler integral, and it's easier to integrate actually. Well, so I mean, these guidelines right here, these strategies can be found on pretty much every single calculus textbook and over the internet or other YouTube videos. YouTubers actually go over this, when discussing this type of topic. Yep.
Are we going to be expected to have these sorts of identities memorized, or will we get them in the class?
I believe the course coordinator typically puts some of them on typically the hardest ones to memorize. But to be in a safer place, I would try to memorize as much as possible. Okay, so let's look at one example to see these ideas in action. So number one, we have the integral of cosine cubed with cosine cubed x with respect to x. Well, in this case, we cannot do the u substitution because, well, if we set u to be the cosine function, the derivative of cosine is negative sine, and unfortunately, we don't have a factor of sine multiplying with the dx, which sends the du part of the problem. So we need to go through another strategy, and that is use these guidelines here. So number one, what do we mean by saving one power of cosine? Well, number one, I will rewrite this integral as the integral of cosine squared, and that saving of power, I'm going to write it with a different color so you can see what we mean. And then the next is to use the trigonometric identity, replace cosine squared with 1 minus sine. So that's the integral instead of cosine squared. Okay, let me indicate how are we going to do the substitution. Cosine squared will become 1 minus sine squared. So that's 1 minus sine squared cosine x dx. And in this case, we are ready to use the u substitution. Why? Because, well, if we treat the u, if we take u, the sine function, what's the derivative of sine? Don't we have that cosine in there? All right, so u equals sine x, not sine squared, du equals cosine x dx, and it's there. That's our use of and how it works. Well, so we will get the following integral. The integral of 1 minus u squared, because sine squared, that's going to be u squared, times cosine x dx, that's du. And well, we only need to integrate this polynomial using general power rule for each. Well, the integral of 1 is u, the integral of u squared is u cubed over 3 plus c, and simply back substitute for the u, which is sine x minus sine cubed x over 3 plus c. Alright, so what did we do essentially? So we did some breaking up of powers. We saved one power to help us set the du part of the problem. And well, in this case, we use identities to change the cosine square in terms of the other function, which is sine squared, whose derivative is a quantity that multiplies with the dx. And that's how we managed to go through this integral. Let's look at another example. Well, the example on the next page The integral of sine to the fifth cosine squared. Oh, well, in this case, what do we have? We have a combination of odd powers and even powers. So, and well, what should we use? Should we use the guidelines for the odd ones or for the even ones? In this case, go with the odd ones right here. Go with the odd ones, because if we use the even ones, well, that's the integral sine to the 4, for example, sine. And then if we use the power reduction formula, there is a problem here. The problem here is that this integral contains trigonometric functions of different angles, and you don't want that, because the u substitutions, when you take these as factors, it doesn't work when you have different angles. So you want to have everything in terms of the same angle. X or 2x, 17x, a million x, it doesn't matter as long as all trig functions have the same angle. So we're gonna go with, yes, I'm gonna save one power of sine in this case, because that's the one that has the odd power. Sine x to the 4th power cosine squared x. I'm just gonna leave alone. I'm gonna leave it alone. So that's sine x dx. Okay, well, in this case we have a sine to the 4th power, but our identity is for sine squared equals to 1 minus cosine squared. In this case, we need to rewrite this first, because this sine to the 4th power is the same as saying, isn't it the same as sine squared quantity squared? Yes, all right. So times cosine squared x and sine x dx. Okay, so this will be replaced with 1 minus cosine squared x, and that's the next step. So that's the integral of 1 minus cosine squared x quantity squared cosine squared x sine x dx. And actually, at this point, we're ready to do the u substitution, because what do we have? We have u as our cosine. We have everything else in terms of the function whose derivative is the quantity I have written in yellow, right? So that's our goal. Use these trigonometric identities to write all the messy integral in terms of a function whose derivative is equal to that factor that we saved when breaking up the powers. Well, so let's see. U equals to cosine. But be careful here. Du, the derivative of cosine, which is negative sine x dx, that means sine x equals to, sine x dx equals to negative du. Okay, so let's do the substitution. This is the integral of 1 minus cosine x, which is actually u, that is u squared, the whole quantity squared, times cosine squared, which is u squared, times negative du. Be careful with this negative. And well, so let's take care of that negative first. Let me write it in front of the integral. And well, let's simplify what we have for the integrand right here. So right here, we are in the need of expanding this binomial squared. And well, you guys have many different tools to expand binomials. Number one, well, it's to write this 1 minus u squared as the product of 1 minus u squared times itself, and then FOIL. That's fine. Maybe that's the way you learn. If it works for you, that's fine. Do it that way. However, there are formulas to square binomials, and let me write it down at the top. Whenever you have a plus or minus b, quantity squared, that's always the first term squared plus or minus, depending on what we have, 2 times the product of a and b plus b squared. And I think it's shorter to do that. It's my advice is to use it this way, especially because this saves time when solving this kind of big problems.
So you have one that is two-thirds and the team, they all have the same third power. How do you can multiply them together?
Yes, so we're going to expand the binomial and then we're going to multiply these together. So that's going to be 1 squared, and then in this case we have a minus in between. That's minus 2 times the product between 1 and u to the second, that's u squared, and then the square root of the second term. What is u squared to the second, isn't it? U to the fourth times u squared du. And then from here, distribute, distribute, distribute. And I'm going to continue here. I'm going to keep the negative for a second. What is 1 times u squared? Well, that's u squared. And then 2u squared times u squared. Isn't that 2u to the fourth? And last but not least, u to the fourth times u to the second. That's u to the sixth du. Okay, before integrating, I'm going to use that negative sign in front of the integral to change the sign of all these terms inside. That way we don't have to worry about too many negative signs after integrating this. So I'm going to change the sign of everything here. That's a negative u squared plus 2u to the fourth minus u to the sixth with respect to u. And well, this reduces to just integrating a polynomial using the general power rule for every single term, right? Nothing crazy. So that's a negative u cubed over 3 plus 2u to the fifth over 5 minus u to the 7 over 7 plus c. We're done with the calculus. The last step right here is to go back to do the back substitution for what we declared for u, which in this case is cosine. So cosine cubed x over 3 plus 2/5 or 2/5 cosine to the fifth of x and minus 1/7, or rather cosine to the 7 of x over 7 plus c. And we're done. Perfect timing.